In this video, we'll be studying about the power of accommodation of human eye. We know that a normal, healthy eye has this unique property to see the nearby as well as the far off objects clearly by forming the sharp image at the retina. In accordance with the lens formula, which is given by 1 upon V minus 1 by U is equal to 1 by F. Now, what is V here? V is the distance of the image from the lens. U is the distance of object from the lens and F is the focal length of the lens. We know that the crystalline lens that our eye has is the convex lens. Now consider the distance between the crystalline lens and the retina. That distance is going to be fixed anyways, right? Because the image is formed at retina. The distance of retina from the crystalline lens is never going to change. That will remain fixed. It is the object distance that changes because when we look in the world or in the atmosphere around us, we see the both nearby objects as well as the far off objects. That too at the same time. So the object distance keeps on changing. Now this variable is fixed, which is the image distance from the lens. The object distance keeps on changing. Then what needs to change to balance this equation? It is the focal length. That is, the focal length of the lens of the eye lens needs to be kept changing in order to ensure that a sharp image is formed at the retina. And this ability of the eye lens to adjust its focal length is known as the accommodation or power of accommodation of eye. This is actually achieved with the help of ciliary muscles which change the curvature of the eye lens so that its focal length is changed. Now let's just see what happens when we see the nearby or the far off objects. When the eye is focused on a distant object, the ciliary muscles are relaxed and the lens is thin. Okay, the object is at infinity. So from infinity, the rays that are coming are almost parallel to each other. That's how we draw them. So parallel rays, they bend as soon as they pass through this crystalline lens because its refractive index is different from the outside. So it is the refraction that takes place. So in this scenario, if you see, the lens is thin, enabling the light rays to focus on the retina at the focal point of eye lens on the retina. This setup makes the focal length of the eye as maximum. Now when the eye is to be focused on the nearby object, the ciliary muscles contract and increase the curvature of the lens. Now if you see in this particular scenario, the width of the eye or the thickness of the eye lens is far more than this particular position, right? So in this case, the ciliary muscles contract and increase the curvature of the eye lens, leading to the lens becoming thickened and decreasing its focal length so that the sharp image is formed at retina. If the focal length was not decreased, this image would have been formed out of the retina, like beyond retina, you can say. That's why the focal length is decreased. Similarly, in this case, if the focal length was not to be maximized, the image must have formed here only, before retina. So, by thinning the lens, the focal length is increased to ensure that the image is finally forming at the retina. And in this way, I can clearly see the distinctly objects situated at different distances from it, forming their sharp images. And this is all about it. I hope this topic is clear to you. Thank you.